Hi, good day, everyone. We'll continue our discussion of the theory of anti-completeness. So today, I hope I will have time to finish these four topics that will lead us to the theory of anti-completeness eventually. I thought next week, but unfortunately, because of reading week and the holidays, actually we won't have class or tutorial for almost 2 weeks. I checked with department by regulation, we should not have classes for undergraduate courses. So I think I will stay with that rule. Okay, so I guess it's good news for you, right? So you can enjoy about 10 days of class free time. Better news? Okay. All right. Yes, and homework 4 will be delayed for, I think, won't be given until maybe next 2 weeks later, maybe, because we haven't discussed these things yet. All right. So, yeah, actually, I don't know whether to say good news or bad news. I don't mind teaching, but when I checked with department, uh, so I think I bet not to teach because some students can complain. Okay. All right. Okay. All right. So let's continue. So last week, we discussed that in order to prove that certain problem difficult, it's good enough to consider decision problems only. So we will focus on decision problems. So that's what we have discussed on Monday. Okay. So we have focused on decision problems. There are a lot of reasons for this. I will give you an example in a minute. So four things I will discuss today. First is input length, encoding a scheme that will lead to input length or size of input. That's actually directly related to why we take a decision problem as our subject. It's also related. Then we'll try to put a formal notion of efficient algorithms. So that will lead us to class P, problems that can be solved in polynomial time. All right. So from input length, then class P. Then in order to prove that the problem is difficult, we need a tool. That tool will be called polynomial reduction or polynomial transformation. Actually, I have seen example earlier. In order to solve a problem, we can reduce a problem to a known problem that can be solved in polynomial time. So we use that idea to give a formal notion of polynomial time reduction. All right. So in order to capture difficult problems, we will introduce a new class of problem called class NP. That's actually related to efficient algorithm, but a different kind of efficient algorithm called the verification algorithms. And then from this class NP, eventually we'll come up with a class of problems that are very difficult called NP complete. So I don't think we'll have time today for that class. All right, so that's a kind of roadmap for today's class. Okay, so let's start with the decision problem. Why do we focus on decision problem? Let me explain reason. Let's go back to our familiar problem of computing Fibonacci number. Usually I spend a lot of time on concepts. My philosophy actually is concepts are really important. Actually, even very simple concepts, it's very difficult to really understand it. Even very simple concepts. Everyone thinks we know these concepts, like time, space, a length, or even money. Do we really understand these concepts? Actually, I don't. I don't at all. Like time, even length. Length, it seems to be very simple. For example, what's the length of line? The length of this line. It seems to be quite straightforward, right? But actually it's not. If you take a closer look at this line, maybe look at this portion, actually it's the not look, it maybe look like this for this portion. If you take close look of some part of it, still it's look like this. So what's the length of this between these 2 points? So I just give you an example. That's why I usually spend a lot of time being slow and on these basic concepts. I really want to get the feeling to understand the reason behind it. All right, so that's why I spend a lot of time on these simple things. For technical part, actually my philosophy is you will be able to actually understand these things by yourself. Just read these things carefully, you should be able to understand it. Frankly speaking, if you don't have ability to do it, then perhaps the computer science is not a proper field for you. All right. So that's my philosophy. Anyway, let's go back to Fibonacci number, how we compute it. So we come up with different algorithm. Anyway, we know, so we can compute this a roughly n log n time to compute n Fibonacci number. All right. So at that time, I said actually it's not a polynomial time algorithm because input length of the problem. So typically what we have is to compute this one, we have input is n. So what's the input length of n? Depends on how we encode the number n. But regardless whether we compute encoded in binary or decimal, its length is proportional to log n. So in decimal, of course, will be log base 10, and in binary, it's 2n. But these two, both of them, it's proportional to log n, all right? So with respect to this input length, then the time n log n is not a polynomial of log n. It's exponential function because n is exponential. So really, the algorithm we have learned to compute Fibonacci number actually takes exponential time. Actually, we can prove it. Any algorithm for computing n Fibonacci number will take time at least. So at least this much. So let me put lower bound notation. Any algorithm for computing n Fibonacci number will take this much time because the output length. So we explained these things earlier in the maybe first or second week. All right. So, however, if we look at decision version of Fibonacci number, so let's take a decision version. So typically, what we would like to answer is whether n Fibonacci number is maybe at least, say, k, for some number k. Perhaps we ask this question. All right, the answer will be yes or no. Now, how much time do we need for this problem? Is it still exponential time, or it becomes polynomial time? Now, what's the input length now? So input will be two numbers, n and k. That's huge difference. Here input only n, but here, other than n, we have k. All right, so input length will be, say, log n plus log k. That's input length. All right. Now, the time it takes. How much time it takes? So actually, we can stop the computation when we reach value k. Right? So we do not really need to compute the full Fibonacci number. Actually, once we reach k, we can stop. So its time actually is proportional to log k part. That's the length of this number k. Once we reach this number, we know whether fn is at least k or not. So we don't really need to compute the full f of n because n can be, actually fn can be much, much larger than k, but we can stop earlier. But the one key point is eventually what we need to compare is compare the number with k. And the k is the input length here actually is k, it's dominated by k. All right. Log k actually is much bigger than log n. Actually, it's here, actually log k will be roughly order of n. So therefore, in terms of time, so if you look at the main cost, maybe just log k. That's the time it takes. I will ignore some detail. TDR. It's also, of course, related to n, but mainly the main cost will be log k. That's a key point. All right. Now, if we compare this log k with input length here is also log k. So of course, here you can say the time actually for computing, time for this part plus this part. All right. But here is only up to k. So we'll compute Fn only up to k. We can stop up to k. So really dominating cost is log k, but log k then is a linear function of input length. Now, so it's the actually computed number takes exponential time, but decision version becomes polynomial. It's actually linear time. So what does this tell us? So if we do not focus on decision problems, then it maybe makes no sense and to consider hardness, because even computing Fibonacci number is exponential time already. So what's the purpose? Is there any problem at all that can be done quickly? So if you look at here, all right. But once we get to decision versions, then it seems, oh, that makes sense, because it's really simple. It's very simple to compute Fibonacci number, and decision version takes linear time. Of course, this also suggests that the actual time, whether we regard it as polynomial time or exponential time, depending on how we measure the input length. All right. So even for Fibonacci number, really depends on how we encode this number n. So if 100. All right. So that's one way to encode it. Okay. So it says its length only 3. So that's its length. But there are other way to encode 100. For example, we can use unary representation for 100. So the encoding will be here the 100 once. But then this time will be linear in the input length. So what it means is actually that learning time certainly depends on the input length, and certainly depends on how we define the input length. What do we mean by input length? All right, so that's actually ask us to fix some encoding scheme first. How do we encode input? So how to represent, that's a very important question. For example, number 10 can be represented by 10 use decimal, and can be represented in 1010 in binary, right? Or 101 internally. So there are different ways. So which one should we use in order to discuss the running time? Because if we say polynomial time, so it depends on which encoding scheme we use. But that's not very good. If our theory depends on encoding scheme, yes, that's base 3. Then our result will not be too general. So somehow we want all our theory to be independent of encoding scheme. So what we want is theory of NP completeness to be independent of how we represent input or encoding scheme. Does not matter how encode our input. So the theory will be same. So with that in mind, what we do is we assume our encoding will be reasonable. Of course, it has to be reasonable, otherwise no sense. We can artificially increase the length of input. Then your running time with respect to input length will be much, as a function, it's much slower growth. So from exponential can become polynomial or even become linear function, because artificially we can increase the length of input, right? So that makes no sense. So what we assume is we have a reasonable encoding scheme. All right. So it's a very simple assumption, just reasonable. So that means uh, so first thing is it's reasonable means it's concise. So we not artificially enlarge the input. So no point. If number is 38, we not artificially make it longer by adding zeros, for example. So padding, so make it longer. All right. So that's called concise. The second thing is decoding. Uh, the encoded string must be decodable quickly, efficiently. So once for an input, so we have input, we have its encoding, so EI, all right? So then we will be able to compute its reverse function easily. So that's what the decoding means, decoding E minus 1I. So that part can be, so that will give us value I. So that part should be done efficiently. So basically, a reasonable encoding scheme assumes these two things. Basically, we're using very natural way to encode the objects. That will be good enough. For example, numbers will be encoded in any base more than one. So we cannot encode 100 with 100 ones. But whether binary or decimal does not matter. And graphs will be represented by a string of vertices and or a list of vertices and a list of edges. And each edge or list, each vertex will be a number. So that number will be encoded in binary or decimal does not matter. And set of objects is just a list of n objects. Each object is encoded in a reasonable way. All right. If you do things like that, then the encoding scheme will be reasonable. And under that reasonable encoding scheme assumption, any two reasonable encoding scheme, the input length will be related by a polynomial. All right. So important thing is with that assumption, we can assume the following. For any two different encoding schemes, so length of encoding scheme E, so that's one encoding scheme. Another encoding scheme is length of encoding scheme and a different encoding scheme, E prime. Their length will be related by a polynomial. So here is another polynomial. So PQ a polynomial. So the actual length can be different, but the difference is will be bounded by polynomial. All right. So everything will be bounded by polynomial. Why polynomial? Because polynomial is robust. In the sense, a polynomial of a polynomial is still a polynomial. You can say that here maybe PQ it's not a polynomial function but n squared, but then this function is not robust because n squared, if we if we replace n by a quadratic function, say 2n squared plus 1, then square them, then you will see it become n to fourth power. So that's not a robust. But polynomial is robust. All right. So that also suggests what we mean by efficiently here. It means polynomial time. All right. So everything now comes with to a polynomial. So we want to distinguish the difference between polynomial and exponential, for example. So actually here means super polynomial, but as an example, polynomial would be different from exponential. All right. So with these things, these idea behind it, so what we want to do is we regard things that are polynomial to be efficient. So here you see it's coming in different ways. So in terms of length, it's a polynomial. In terms of encoding, decoding time, it's a polynomial, and so on. All right. So with these concepts, then we can come up with what we mean by efficient algorithm. It's very naturally come to efficient algorithm. The concept of efficient algorithm. So what type of algorithm should be regarded as efficient? So if you understand the idea behind the encoding scheme, the length of input, it's very natural that that will lead us to running time is bounded by polynomial of n. So P is a polynomial. So that's P is a polynomial. Sorry, it's a space here, not enough. So let's just here the polynomial. Okay. So what we mean by efficient algorithm is a polynomial algorithm, polynomial time algorithm. All right. Now, that's only for theory. Okay, let me emphasize one thing that's very important. The theory of NP completeness, main purpose is theoretical. For practical reason, polynomial time does not make sense, actually. In practice, anything more than n squared will be useless, almost useless in practice. So in practice, in order for your algorithm to be useful, its running time should be less than n squared. Typically, it should be n or n log n. Otherwise, it won't be too useful in practice because normally n is huge. Of course, for small n does not matter. If 1,000 or so, usually does not matter. So n may be in billions or something. All right. Also, in practice, polynomial algorithm does not mean it's really very fast in practice. Even one algorithm say it's exponential 2 to the power n. One is polynomial, but n to power 10s. All right. So in theory, this one is much better. But in practice, it's not the case. Only when n is at least, say, 59, since this one is always better. Sorry, this 2 to the power n is always better than n to the power 10s, unless n is at least 59. So in practice, a different issue. Okay, so the theory of NP completeness is really theoretical. It will give us a guideline. So in practice, we have to consider other things. All right, but anyway, now it's not big. Yeah, it's not big, but for many problems, maybe n is very small. It's possible in practice. For larger problem, of course, but even that's the case, you're dealing with large n. But eventually, in order to solve a larger problem, you break it into small subproblems. But once you get to small subproblems, say n equal 40, so then you should not use this one. You should not use this one. Rather, you should use this one when n, say, is at most 59. It's better maybe use this one. All right. So it's really theory and the practice may not have very often they are different things. All right. So you can use theory as guideline, but don't be just strictly following the theoretical things. In practice, they may not be that useful. Everyone knows that, right? It's just theory. Okay. Okay. So, but going back to theoretical parts, so we know that efficient algorithm will mean polynomial algorithms. Now we can define the first class of problem called class NP. Class P. To capture problems that can be solved in polynomial time. So this P equal all problems. Of course, as I said, we focus on decision problems. So this problem is decision problem. All right, this problem admits a polytime algorithm. So that's what we mean by class P. So strictly speaking, class P refers to decision problem only. But in practice, as a convention, any problem that can be solved in polynomial time, we can say it belongs to class P. For example, minimum spanning tree problem, shortest path problem. Actually, none of them are decision problem. But typically, we say minimum spanning tree belongs to class P. It's okay. Everyone understands what we mean. All right. So in practice, again, in theory, class P means it's only referred to decision problems. But in practice, we also refer to other problems that can be solved in polynomial time. Normally, that will not cause any confusion at all. All right. So now we know what do we mean by efficient algorithm. So we have a mathematical notion of efficient algorithm. So efficient algorithm means problems that can be solved in polynomial time. And strictly speaking, that refer to decision problems only. So in practice, any problem that can be solved in polynomial time, we can say it's in class P. All right. Okay. Okay. So we finished this discussion of half a page for how many minutes? 20 some minutes. All right. No, don't worry about that time. All right. So now let's go back to our original purpose of the NP completeness. So far, we haven't touched it. We just defined easy problems, set up problems that can be solved easily. So now going back to the original purpose. So what we want to do is actually to prove some problem is hard. To prove certain problem difficult to solve. All right. So typically we have a name for a hard problem called intractable problem. So what we mean by intractable, a problem not belong to P. Then we call it intractable. So that do not have efficient algorithm. Again, strictly speaking, it's referred to decision problem only. But in practice, any problem that cannot be solved in polynomial time, we can say it's intractable. But be very careful here. Computing nth Fibonacci number, no one will say it's intractable. So it actually takes exponential time in terms of input length. So here, sometimes you have to make a decision whether we should really refer to decision problem or not. But for computing nth Fibonacci number, no one will say it's intractable problem. So actual time, any algorithm for computing nth Fibonacci number takes exponential time in terms of its input length. All right. So that's one part of computer science. Even theoretical computer science, it's not as rigid as mathematics. So that's something different. And most part is mathematical, but it's not as rigid as the mathematics. It's purely based on a system of axioms. It is not the case in computer science. So a word of warning, all right? But usually that will not cause too much trouble, all right? So how do we prove hard problems? Of course, ideally, we would like to have absolute proof. For example, actually, we can prove that certain problems even do not have algorithms. So actually, we can prove that there exists problems there exist problems that cannot be solved by any computer at all. We can prove it mathematically. I don't know whether you learned these things. For example, the halting problem, the famous one is the halting problem. So these problems are called non-computable. All right. So actually prove that certain the halting problem cannot be computed. It's very simple, use diagonalization. So I give you a program and give you an input string, ask whether this program input on this part, sorry, it will eventually stop on this particular input. Actually, this problem is uncomputable, cannot be decided automatically by any algorithm at all. So we can prove something like this very rigorously. However, to prove that some problem cannot be solved in polynomial time is not easy at all. No one really knows. Actually, no one knows how to do it. Prove that a problem cannot be solved in polynomial time. There are some problems, but for most common problem, we would like to have polynomial time algorithm. For example, the subset problem, a clique problem, vertex cover problem, longest path problem. For these very common or normal problems, daily problems, in order to prove that they do not have polynomial time algorithm. Actually, we don't know how to prove it at all. No one knows. Anyone know it will be extremely famous instantly. All right. So how can we accomplish this task to prove that certain problem are difficult? So since I said that it's almost impossible to prove in absolute terms that these problems are difficult. So what can we do? Actually, we can use a daily idea from daily life, as I just said, famous. How do you can prove that you are famous? If you want to convince your friend you are famous, so I'm famous, how can you convince the friend? One way is you said you know some famous people, right? You made famous person. Maybe you said, "Oh, I made a call to Andy Lau, Lau Dawang." Okay, so you can say, "I made a call," right? And maybe many friends or some friends of you will be convinced, "Oh, you are very well known. You are famous, right? You know Andy Lau." But actually, that's not the right way. Actually, it's logically it does not make sense. Actually, it's not quite right because anyone knows can find his phone and make a call. Does not matter whether he answers you, he talks to you, whatever, right? You can make a phone. Does not matter. Actually, it's not the right way. Right way is what? To prove that you're famous. Uh, you may maybe I'm not using I. Okay, better use because instead I, it's maybe you. 老多 made a call to you yesterday. Of course, you can emphasize anyway. You chatted for half an hour, whatever. But this message alone will be good enough, right? If you are not famous, why 老多 will call you? You must be very well known. You are famous, so 老多 is called you, right? So that's one way to do it. So we can borrow this idea to prove that certain problems are difficult. So compare with famous, we want to prove that intractable problem. We can use this idea. Intractable. Okay, suppose I know that one problem is difficult. I don't know how to prove the first one, but suppose I tell you that I have a seed problem. This, suppose I give you a seed problem. This particular problem. All right. Now, how can we use this seed problem to prove that your problem is difficult? So I give you this one, and the question is how to prove. All right. So how can we do this? Make a comparison of a call from Lao Dewa to you. So famous here. So here, if Lao Dewa made the call to you, that will prove that you are famous. Now, how can we use this idea to show that pi is hard? All right. So suppose I give you C the problem, difficult problem already. So, I don't need to tell you how I prove this problem difficult. I only assure you that pi star is a difficult problem. How can you use this fact to prove the problem pi is also difficult? So we use the analogy here, sorry. All right. So So in order to convince other people that you are famous, what you did is Laodoa make a call to you. Now, in order to prove that your problem is difficult, the hard problem make call to you, for example. So, but of course, this call is something different, right? So this hard problem calls you. So causing means what? Maybe perhaps hard problem want you to solve the problem by solving problem pi, asking for help. So you can regard this one as this one asking for help. This problem for help. Or if Laodoa make a call for you, asking you for help, of course you are very famous, right? So we use the same idea here. All right. Do you see the analogy here? If you see that, you can erase that Laodoa part. Okay. All right. Okay. So that's how we are going to do it. So the idea is, so this call means what? If pi can be solved in polynomial time, then pi star can also be solved in poly time. So that's the meaning of this call. So in order to prove that pi is also difficult, we can use this idea. If I can prove that exists some kind of call from pi star to pi with the following property, then that shows pi is also difficult, because otherwise I will be able to solve the difficult problem. But by the fact that pi star is difficult, we know then pi cannot be solved in polynomial time. So that's contrapositive means if pi can be solved in polynomial time, then pi star can also be solved in polynomial time. That is contrapositive. All right. So here it's 2. So that is contrapositive. Otherwise, in other words, it means so the same as equivalent. These two logical statements are equivalent. If pi star is intractable, then pi is also intractable. So these two are logically equivalent. They are contrapositive to each other. All right. So now let's give us a hope. So if we knew that the seed problem for intractable problems, then we're able to use the idea of call to develop a tool to show that other problems difficult. So now what do we need for this call? All right. So what do we need for this call? So what does this call mean? Means reduction or transformation. So what happens is we reduce or transform pi star to pi. So what this call means, right? We reduce this difficult problem pi star to your problem pi. We have seen it when we try to solve a problem. We reduce a problem to a different problem. For example, two-set problem. In order to solve two-set problem, we reduce it to a strongly connected component problem in a digraph. So that's a reduction or transformation. All right. Now, in order for this one to hold, this equivalent problem to hold, What is required in the reduction or transformation? What properties do we need to have for such transformation? What we need for reduction or transformation? What do we mean by efficient here? It's polynomial time. So in order to carry out these things in polynomial time, what we need is reduction and transformation takes polynomial time. Because polynomial is still polynomial. So if we solve this one in polynomial time, say Tn, and the transformation takes polynomial time, say Qn. All right, so total time will be Qn plus P. Now this n, the length may be changed, but at most Qn. So total time will be this one. It's still a polynomial. So you see the robustness of polynomial. All right. So what we see is this transformation should be done in polynomial time. Okay. So now the notion of polynomial reduction just popping out. So here comes the formal definition of polynomial reduction. So once you understand these ideas, it's naturally you can come up with this polynomial reduction. But that's the most important part of theory of NP completeness. It can be called a reduction or transformation. All right. So from one problem to another. So first problem to second one. Typically, we denote it. You will see in textbook, I think it's uses notation less than equals and put a p here. Polynomial reduction means. Usually, I would rather write this way. In Geller and Johnson's book, the Bible of NP completeness, they use this notation. So usually I will write in this way. All right. So that's notation. So that one is a polytime. So this polynomial time function, of course, is from first problem to second problem. So that's domain of first problem to domain of second problem. All right. Now, of course, this is not arbitrary function because the purpose is if I know how to solve problem pi 2, I know how to solve problem pi 1. So what is required, the key requirement is, of course, for every instance of the first problem, actually should write in the domain, okay? In notes, I just write in ground pi, so it's a building of notation. So for each instance of the first problem, instance of problem 1, if only if it is the image is yes instance of second problem. All right, so naturally you come up with this notion. So basically the answer here is yes, then the answer here is yes. So yes corresponding to yes, no corresponding to no. So after reduction, in order to solve the original problem, you don't need here, you just solve problem pi 2. So you just solve this instance for problem pi 2. If answer is yes, then you have yes. If no, then no. All right. So that's the notion of polynomial reduction and transformation. And that's extremely important. All right. Okay. time is up already, but it's okay. I think these ideas is very important. These concepts are really essential. I would rather slow because I think the theory of MP completeness may be the most difficult part for many students. So I would rather slow and really help you to understand the concepts. All right. So I think, yeah, I don't even have time to give examples of reductions. I will do it after the long holiday. Okay. All right. So any questions? Do you have a basic idea why we developed the theory of NP completeness in this way? Get the idea of what's the key idea behind the notion of polynomial reduction. So hope it will help you to really understand, to appreciate the theory of NP completeness. There are a lot of things actually behind it, why we do it in this way. All right. Okay. Okay. So enjoy your holidays. You have about two weeks break. So I will talk about, we'll give you examples and then class NP verification algorithm after the break. All right. In the meantime, I would like you to read something easy to understand some problems. So later on, when we discuss reduction between these problems, I don't need to go to details. So I'll put that in the course homepage. All right. Yes and no, actually. The time is almost, it's okay. Just I will certainly have time to finish NP completeness. That part certainly do have time within normal time framework. Just after that, approximation algorithm and FBT algorithm, that part may need to be cut short. I will see. Maybe we'll give additional lectures during class makeup week or even after that. Does not matter. One nice thing about online thing does not matter. I can just add these things up. But of course, internal exams maybe will be covered only to normal lecture time or something. All right, that's the only thing different. Internal knowledge, don't worry. I will certainly teach you enough for algorithmics. All right, okay. Yeah, initially I have a lot of time, but suddenly the 2 weeks takes away all these things. Originally, actually thought of adding some material from the elite session, something quite interesting. But I guess certainly won't have time for that part. All right. So thanks. Yeah, I think that's it. Thank you. Yeah, we'll see you after almost after 2 weeks. All right. Okay. Bye bye.